Hi, good afternoon everybody, and thank you Fraser for introducing me. My name is Mick. I'm CTO and co-founder of 𝗖cie, and today I'm going to talk about ATHENA PICO, which is a 1P electric space thruster for pico satellites. So at 𝗖cie, our mission is to build innovative, tailored, end-to-end space mobility products and services for the next generation of small satellites, empowering a sustainable new space economy. So a little bit about the company. I'll keep it short, but I think it's important to mention. It was founded by my colleagues Daniel, Sarah, Javier, and myself 6 years ago. We all come from different backgrounds, mainly in electric propulsion, but also micro systems. And we started out with 4 people, and currently we are 30 people in total. Our headquarters are based in Madrid, in Spain, where we have our offices and some clean room facilities, vacuum chambers for testing. And then we have some people embedded in microfabrication centers in Barcelona, also in Spain, and in Uppsala in Sweden. So what are these space mobility products and services that I mentioned? So we have what we call an end-to-end ecosystem of propulsion products and services. And so far we have 3 different ones. 2 of them are software, which are 𝗖cie and Orbital. And one is ATHENA, which is our hardware product. I'm going to mainly be talking about ATHENA, but I'd like to mention 𝗖cie a little bit because I think it might be of interest for some of you guys. So 𝗖cie is a mission analysis software that can be used for both direct and indirect problems. So it's a propagator, but it can also be used for design. So that's what I'm mentioning here. So yeah, so direct problems, which is just propagating in orbit, whether with or without propulsive maneuvers. But you can also solve inverse problems, which are useful for design, for concurrent design, and for optimization. So how does this work? It's a self-contained software that runs on the cloud with a Python client. It has a user interface, and initially you define an environment. You choose the relevant planetary motions, Earth rotation models, sun models, space environment settings, so which kind of density models you want to use, if you want to use any kind of gravity models and which ones, so that you initialize. And of course, the better the model, the higher the fidelity, the slower the computation, but you can get really, really accurate results. Then you define objects, time and reference frames. You define orbits, attitudes, ground stations, if those are of interest to you. And lastly, one or multiple spacecrafts with the subsystems. And it has a database of COD subsystems that are modeled already, coming from the provider, but you can also have user-defined models for your subsystems. And then lastly, you define behaviors, which are different operations. An operation has a mode and also has events. And modes can be pointing, propulsive modes, or certain subsystem behaviors that you want to model. And then there's events, which has triggers and effects. And triggers can, for example, be at a certain point in the orbit, do X, or when I'm inside of a ground station, do Y. Or for example, when my battery charge goes below 70%, do something else. So these kind of continuous and discrete triggers can be taken into account as well, when you propagate and even when you do optimization and run the optimization algorithm. So what do our clients use 𝗖cie for? So for analysis, this is the simplest case where you just propagate in orbit and see what it looks like, what happens. And you'll see some examples of that later. But also for design, for example. I'm not sure you can see it here, but this is a trade-off between propulsion and electrical power system. So perhaps you want to have larger solar panels to have more power, but then your drag will go up and you might need a bigger propulsion system to compensate for that. And then you're using more power. So it's not clear that bigger solar panels necessarily are a better option. So these kind of trade-offs, like how does adding more solar panels affect the rest of my system, is something that you can analyze with this software. And you can get these nice Pareto fronts where you can do trade-offs between propellant and maneuver time, or between for different subsystem sizes. And you can do all these kind of trade-offs that really lets you do concurrent engineering of your system. And lastly, optimization. So once you have a design, you do want to have an optimized orbit, and you can basically calculate what would be the ideal operation of your spacecraft, taking into account propulsive maneuvers. to make the most of the propellant that you have. And taking into account all the operational constraints that you put on your mission. For example, I need to point to the ground station. These kind of constraints you can take into account. So that was regarding 360. What I want to talk about the rest of the presentation is ATHENA. And ATHENA is a family of propulsion systems that we're developing. And we develop those particularly for small satellites. And when I say small satellites, I mean pico, nano, and the smaller end of microsatellites. And so when we were developing this propulsion system, for us, the drivers, or the obvious drivers, were the following. So low power, because there isn't that much power available in only small systems. High efficiency, mainly because people have tried to scale down existing propulsion technologies to small scale, and you lose basically all of the efficiency. So it's important that with the little power that you have, you do actually generate thrust. So high thrust to power, because for us, I think speed of maneuver is more important, or it's not just for us, for most clients, speed of maneuver is more important than saving a little bit of propellant. Low thermal loads, because those are very difficult to manage in a small spacecraft. Manageable, safe, green propellants. Nobody wants to have to deal with the protective gear to load a hydrogen into a thruster. Very compact systems, and something that's scalable and modular to deal with all the different platform sizes and shapes that are out there. So for that, we came up with ATHENA, which stands for Adaptable Thruster Based on Electrospray Powered by Nanotechnology. And I'm going to explain how this works. So there's a nice infographic, but I'll be doing the voiceover. So our thruster works with ionic liquids, which are basically synthetic molecular ionic salts that are liquid at room temperature, and they consist of positive and negative molecular ions. And these are stored in what we call the propellant buffer, which is like a porous reservoir that stores the propellant. And so this is the buffer. And then on top of that, we have something that we call the emitter, which is basically a microstructure, a needle-like microstructure in the order of hundreds of micrometers. And it's covered with a nanotexturization layer that allows for wicking the propellant from the buffer to the tip of the needle. And the other critical component is the extractor electrode, which is a conductive grid that is aligned with these needles. And then we apply a very high voltage between the emitter and the extractor. And this creates a very intense electric field at the tip of the needle, which allows us to extract ions from the liquid and then accelerate them in the voltage drop. And this generates very high velocity jets that in turn generate thrust. And when I say high velocity, 30 kilometers per second or more. And so one tiny microscopic needle doesn't generate a lot of thrust, but you can multiplex them into arrays. They're basically silicon chips with many, many needles. And then we can then put more or less of these arrays on a thruster. So this makes it very scalable. So you can have thrusters with 2 of these arrays, or 4, or 6, or as many as you can fit. And then, of course, these thrusters can then be clustered. So for larger satellites, we could put 4 thrusters, for example. Apart from the thruster unit, you also have that's what we call the PMU, the propellant management unit, which is basically a bunch of tanks that store the propellant, and the power and control unit, which are the electronics. And all this is housed in a aluminum enclosure. So that's the thruster in a nutshell. As I mentioned before, it works with ionic liquids, which are a very particular class of materials. As I said, liquid at room temperature, stable in vacuum. They have positive and negative ions, and if you emit both, then they're self-neutralizing, and you don't need a cathode, which complicates things a lot and costs extra power. They're non-toxic and safe, and this can be manufactured in any lab in Europe, in the US, wherever you want, as opposed to, for example, xenon that's currently mainly obtained in China, Russia, Ukraine, which because of the geopolitical situation is difficult to get. Prices have gone up a lot. So using these kind of propellants promotes European and US non-dependency of the supply chain. As I said, ATHENA is not just a thruster, it's a family of propulsion products. So we have 3 of them. One is ATHENA Nano, which is this one, which you might recognize from the video before. It's focused on CubeSats, on nanosatellites. These are the current specs. We hope to be able to increase the power a bit more in the future, but about 200 to 600 micronewtons, 1500 newton seconds of total impulse, and about 8 watts nominal. But, and I think of most interest to you guys, we're started now recently working on the ATHENA Pico, which is basically a scaled down version of the Nano, has a similar or the same technology. minus some components. These are the specs. About 70 newton seconds of total impulse, relatively low ISP, 350 seconds, which is something we're working on, but relatively high thrust, about 200 micronewtons, so similar to the Nano, even though it's much smaller. And the max power is about 4 watts, nominal expected to be about 2.5. Even though these specs will be improved in the future because they're not what we're aiming for, this is already a useful thruster, as you will see later. And then hopefully next year we will also kick off development of the micro, which will basically be a larger version that is focused to the smaller end of the microsatellites with around 100 watts of power per thruster. So this is ATHENA Pico. This is a render of the actual design. The only thing that's missing here is the components on the PCB, which we're still populating. But otherwise, this is what it's going to look like. It basically has a peak housing with 2 small thrusters in it. So these are the extractor electrodes that I mentioned before. The dimensions are 45 by 45 by 50 millimeters. So they snugly fit inside the 3P, for example, taking up about 1P. And these are the specs. Efficiency is relatively low, I'd say, but still higher than most other systems because we need to heat the propellant and a lot of power goes to heating. The propulsion itself is actually relatively efficient, close to 50%. As I said, total impulse 70 newton seconds. That limits a bit what you can do with it. Nominal power 2.5, and thrust is variable depending on the operating point you choose. Operational time, this is meaning active thrusting time, about 300 hours so far demonstrated in a lab environment in a vacuum chamber. And so what's mainly limiting here is the ISP, which is relatively low for electric propulsion. This is closer to a very good chemical thruster. And because this is low, this limits the total impulse. We hope to be able to at least double, if not triple, this number on a future version. But that requires some engineering. So what can you do with a thruster like this? So we analyzed some use cases. If you remember a talk from this morning from iTech, they've been looking into propulsion, and we are provider number 1. And as part of the conversation we had with them, we did some simple analysis using 360 to show what you can do with a thruster like this. So one of the proposed concept of operations was launching from, or at least in an orbit similar to the ISS. And this applies some operational constraints because you're not allowed to be in that same orbit because you're a danger to the ISS. So you would have to do some initial orbit raising, then some station keeping, and then you can optionally do some deorbiting or just directly do a natural decay. So the cases that we analyzed, we looked at a 6P thruster of about 1.5 kilos. There are 2 different areas depending on the attitude of the satellite. And then we looked at 12 gram and 24 grams of thruster because at the time we didn't know how much we could fit, and now we know it's closer to 20 to 24 grams. Here you see some of the results. So here you can see the initial orbit raising. So you can choose how much orbit you raise as the first maneuver. So you can go with 12 grams up to 40 and with 24 grams up to 80. If you go up to here, that means you spend all your propellant and the only maneuver you did is orbit raising. And then based on the orientation of your satellite, you can have a lifetime that is somewhere from anywhere between 100 or less than 100 days up to almost 3 years, depending on orientation and the amount of propellant that you carry. This is a limit case where we looked at. So here, for example, this is what if I do just station keeping until my propellant is empty versus I maximally raise the orbit at the beginning and then let it decay. And this is for the 12 gram propellant with the worst case ballistic coefficient. And so here you say that the lifetime is about similar, 270 days versus 290. So here I stay at the same orbit as the ISS, which wouldn't be allowed. But for about 4 months, you can maintain the orbit, and then once the propellant is gone, you start to decay. And here you have your orbit raising 40 kilometers right at the start after commissioning, and then you let it decay naturally. In the event the lifetime is similar. The only benefit here is that you introduce a right, essentially, of the ascending node shift with respect to the other case. So you're basically moving away from the ISS. So this is safer, for example. Also, what's interesting, so even if you move away, so you say there is initial orbit raising, so I'm good, but that's not necessarily true, and this is not trivial, is that once you come back down, you need to know what is the route, because you will cross again, the orbit of the ISS, and you need to know what is my RAN shift between my orbit and the ISS when I cross the orbit. So that's something we analyzed here. You see in purple basically the steady altitude of the ISS, and then in turquoise you see the decaying altitude of the thruster on the way down. These are the RANs of both, and here you can see the differential distance between them. So here it's 0, so this is where they cross, as you can see here. And here this is the RAN phasing between them at the moment of crossing, which is 7.5 degrees, which is relatively close. Imagine there's a large error on that, so this is not that far away. And this is if you do an original raising of 40 kilometers and then let it decay. In this case, you do an initial orbit raising of 80 kilometers, and then once you cross, which in this case is somewhere here, the RAN shift is 45 degrees, which is appreciable. So even if you choose to do initial orbit raising to get away with the ISS, when you come back down, you need to check the RAN phasing. And if it's very close, you might actually want to have to do some kind of deorbiting maneuver to increase or decrease that. These are all kind of non-trivial things that you may not think of if you don't use software like this. The other proposed concept of operations is a rideshare case. Historically, that's been for Pico satellites 500 to 550 kilometers SSO orbits. So you can see some data. So we assume that that would be the case here as well. So we choose 500 kilometers SSO, and then you don't have a constraint relative to the ISS anymore because you're no longer near it. So here you have so this is for the high ballistic coefficient, so low drag case, just the natural decay. In this case would be 4.2 years from a 500 kilometer orbit for a 6P oriented in a certain attitude. And then here we propagated 6 months of orbit maintenance, and you can basically see that you have about a constant 0.35 grams per month propellant consumption, and this you can basically extrapolate to the rest of the mission. So here you can see, okay, the more propellant I spend on station keeping, how much more years can I expand my mission? So we said 4.2 years natural decay. And so the more propellant I spend, the longer I can maintain my orbit. So basically you can get to very large or long lifetimes using the thruster. So these are, decay maneuvers. So maybe you want to do some deorbiting. And generally at 400 already, you decay relatively fast. But at 500, it may take up to 4 years, and maybe that's too long. Maybe you want to decay faster. Or maybe you want to have some control decay because you're afraid of running into something else. So 6 grams reduces your decay time to 2.9 years. And if you would use all 24 grams for the orbit maneuvers, your decay time will be reduced to less than a year. So you can see here the driven deorbiting and then natural decay. And so of course, the greater the propellant you spend on deorbiting, the faster the decay time is, obviously. So what you then can do, for example, is one of these trade-offs. Okay, how much propellant do I want to spend on orbit maintenance, and how much do I want to spend on deorbiting? So here you see this trade-off. So the left side is 100% to deorbiting and none on station keeping, and here it's 100% station keeping, none on deorbiting. The way we define it here is that in 1 year, you decay about 15 kilometers from your original orbit, and that we call nominal, and then beyond that, you start decaying. So you have about at least a year if you do nothing, and then with the station keeping, you extend that. And so you can trade off the decay duration versus the useful mission duration that you have based on how much propellant you allocate to each maneuver. And of course, you can make this much more complicated because maybe you want to add an orbit raising, maybe you want to keep some reserve for collision avoidance and any other kind of operation you want to do. Especially if you want to do constellations, you might want to do some initial in-plane phasing because you launch together and you want to space them out. So you can do these kind of trade-offs in a much more complex way with the 360 software. So as you can see, you can already, with the tiny thruster with specs that are not yet, let's say, state-of-the-art, you can already do interesting things and extend your lifetime. And the question here you have to ask yourself, okay, what's more expensive, a thruster or launching a new satellite from scratch? So that's a bit the trade-off for clients, I think. So to summarize, I talked about ATHENA PICO, one Pico satellite thruster that hopefully is ready by the end of 25. It already has useful specs that you can actually have an impact on your mission positively, and will have improved performance in the future. I talked a little bit about 360, a mission analysis and optimization and concurrent design tool. that might be of interest to you guys. And then that propulsive concept of operations planning is not trivial, and there's trade-offs to be made in these cases. And lastly, I wanted to mention regarding 360, because I think there's quite some universities here. We do have educational licenses. For example, the Polytechnic University of Valencia and of Madrid are using it, as is the Air Force Academy of Spain as well. So in case any of you is interested in that, I'm happy to chat about that. And that was my talk. Thank you very much.